Hey there, folks. Back here with just another quick example. Um, Following up with from the last video where we introduced the epsilon delta definition of a limit. We looked at a quick example at the end of that pertained to proving the limit's value for a linear function. What I want to follow up with is showing you one more case for a little bit more of a complex situation and what does occur in these calculations. There's a little bit more complexity and is a proof for a quadratic function. Right here, I'm going to show you the proof for a quadratic. And I did separate it out here. Uh, it's a long proof. It's kind of a longer proof. In the end, it takes up some vertical space. That is for certain. Just because of the way it lays itself out. But it's about 3.5 pages once it fills that space. So bear with me on all this. Certainly, I think if we condense this linearly on top horizontally, it would probably take up a lot less space. But it is drawn out with that vertical mathematical style. So it's a long proof here in the end, nonetheless. But here we want to prove, and I have this limit of a quadratic function. The limit as x approaches 2 for 3x squared minus x plus 1. And we can see that equals 11 through substitution, right? Plug in 2 for x, and you can see x squared, right? When substituting in 2, you'll get 4. 4 times 3 is 12. 12 minus the 2 is 10, and then add 1 to that, you get 11, right? So we can run upon 11 pretty quickly in the evaluation. Where we want to spend our time, though, is proving that result is true, right? And again, what does that mean in the epsilon delta definition? Well, that we need to show for every epsilon greater than 0, there exists a corresponding value at delta greater than 0, such that for the absolute difference between f of x and L, that's less than epsilon, whenever we start with the absolute difference between x and 2 being less than that value of delta. All right? This is what we're going to need to show is true with the epsilon delta definition of this limit. All right? And it's a little bit more involved than the linear case. It does begin the exact same way, and that is with the preliminary algebra. As always, a little bit of preliminary algebra is going to show you the path. It's going to give you the path you're going to need to move from this statement here to this statement here. Right? Not only are you going to have to, in this preliminary algebra, determine how does delta relate to epsilon, but what you also have to establish is what's going to be the path that's going to allow you to move from this statement to this statement using that relationship between delta and epsilon. All for this case specifically. All right. Let me show you how that's done. Again, the algebra starts off the same as it did in the linear case. You're going to look at the epsilon statement, begin where you're going to end in the proof, and say, how can I manipulate this to give me something that looks like this? And this is really the key. If your limit value is correct, this can be done. If the answer to your limit is incorrect, this cannot be done in these first few parts of these steps. Right? Think about it here. We're going to start with the value of f of x and take away what we evaluate as that limit. When we do that, we end up with 3x squared minus x minus 10 in value, because 1 minus 11 is negative 10. That argument inside the absolute value simplifies into this statement here. Where that statement there then factors itself into this statement here. We can factor that into the product of the linear factors 3x plus 5 and x minus 2, where, hold on, x minus 2 should ring a bell because it is the value you're searching for right, to begin your proof, the absolute value of x minus 2. Notice that would not occur if I was to use some other result for this limit. If I was to say instead that this was the value of 12, right, and I have 12 in here, this result down here would have actually been negative 11. And if this was negative 11 down here because this was 12 right here, right, this would not factor into that statement there. This is where it really comes together in terms of this wouldn't be true, what we're going to be able to show in the following, if this little bit doesn't happen. All right, so let me go back and fix all that, because that's what needs to be true. All right. Now with this statement here, we can do something very similar to the algebra we've done above. All right. We can factor out the absolute value of 3x plus 5 from the absolute value of x minus 2, and then we can divide it from both sides. Right? Remember, the absolute value will distribute itself across these two factors. All right? We could almost think of it as that in the previous step. Right? And dividing by the absolute value of 3x plus 5 moves it over here to the right-hand side, underneath the epsilon. And notice what we end up with. We end up with a statement of it. The absolute value of x minus 2 has to be less than epsilon divided by the absolute value of 3x plus 5. And this statement here is going to start to give us some direction as to how we're going to choose our value of epsilon, or our value of delta that corresponds to epsilon. We are not, however, going to be able to choose epsilon divided by the absolute value of 3x plus 5. Making the choice with this value for delta has an issue because this doesn't just work for every corresponding value of epsilon. This value of delta also depends upon location for your independent variable x. So this value of delta doesn't stay consistent for every given value of epsilon. It also depends upon location. And that is not what we can establish in our proof. We kind of need to eliminate that variability in the proof, the variability that x could have an influence on our value of delta. And we can do that because really what we're dealing with are inequalities. Because we're not solely dealing with equational relationships here, and we're dealing with things being bigger than or smaller than each other, right? If we can establish that things are bigger or smaller than other things that are bigger than smaller than other things, then we can figure out other inequality relationships with all those items, right? Like if I can figure out what this might be bigger than, or be careful there, smaller than in terms of epsilon alone, right? I can then choose that value for delta and be able to make the statement that this is also true where absolute value of x minus 2 is less than that epsilon over that value of delta. Well, that chosen value of delta, I should say, that relates to just epsilon. All right. So how do we do that? Well, we make some assumptions. I believe this is where we begin with a bit of an assumption. All right. What we do is we establish basically an arbitrary choice. Well, maybe I should say this. An arbitrary bound for epsilon that takes our choices for delta and gives us some options. Maybe that's how I want to say it. And the way we establish that choice is by putting some limitations on delta to begin with. All right? Delta, what we're always going to probably want to start to assume about delta, when we go to choose our value of delta that corresponds to a given value of epsilon, right? we want to note that a good choice for delta is usually going to be pretty small. Chances are that when you're given a value for epsilon and you're talking about being arbitrarily close to L, you're probably talking about being really, really close to L, being really, really infinitesimally close to L, which means your delta is also going to be very, very small, almost probably infinitesimally close to L, or A, I should say, in value. So that's a safe assumption to make to begin with here, that delta is less than or equal to 1. All right? If we set up a boundary there and we make that assumption, then there are going to be choices for epsilon that give us a delta outside of a value of delta that's greater than 1, where if we still just pick a delta less than or equal to that value of 1, we're going to be safe in our choice. Our implications are all going to be the same. So assuming delta is less than or equal to 1 does have some implications. Right? In the statement, the absolute value of x minus 2 being less than delta, then, we can say that that absolute value of x minus 2 must be less than or equal to 1. And the absolute value of x minus 2 being less than or equal to 1 implies, or we should be careful there, delta is less than or equal to 1. The absolute value of x minus 2 then being less than delta would actually be less than 1. And if it's less than 1 in its absoluteness, removing its absoluteness means that it's actually between -1 and +1 in value. Remember those absolute value rules for solving absolute value inequalities. All right? For an absolute value to be less than a number, the argument of the absolute value must be stuck between the positive and the negative of that number, which is what we see here. Where now if we add 2 to the inside to make it x, we can add 2 to the left and the right sides to make the statement x must be between 1 and 3. Right? If we make this assumption about delta, we can make this assumption about that value of x, the independent variable of our function. The same x that we see here or here or here, right? We can say that that x must be somewhere between 1 and 3 if delta is chosen to be less than or equal to 1. Now, if delta or x is stuck between 1 and 3, that means 3x plus 5, that value stuck underneath epsilon here in this conclusion, must have its relationship and have an inequality related to it. And what it says, if we multiply that by 3, 3x must be stuck between 3x and 9. Well, if we multiply that by 3, 3x must be stuck between 3. Multiply that by 3 and this by 3, we would get 3 and 9. And then if we add 5 to that 3, we would be at 8. And if we add 5 to this 3, we would be at 14 in value. So for the absolute value of that quantity, right, if the non-absolute value is stuck between 8 and 14, well, its absolute value will also be stuck between 8 and 14, and we can conclude this for the absolute value, is that it in turn is also stuck between 8 and 14. Right? So for the value, the absolute value of 3x plus 5, we see underneath the statement here, since x is stuck between 1 and 3, right, that ends up implying that 3x plus 5 must be stuck between 8 and 14. And for the value of epsilon divided by the absolute value of 3x plus 5, it must be stuck between the epsilon value of 14 on the low end and the epsilon value of 8 over 8 on the high end. Now notice, what we are doing is we are dividing both of these arguments by epsilon. We are dividing everything by epsilon. All right. Excuse me. On both sides. Just to explain some of the work here. But then when we reciprocate that interior argument, right, we are able to reciprocate that and involve the absolute value again, because it's also going to be between 8 and 14. These outer boundaries are going to reciprocate. And not only reciprocate, they're going to change their value in terms of the inequality. 14 times or divided by epsilon being bigger than this is actually going to become smaller than it when we reciprocate the arguments. All right? So that's what we see occur in this result. Excuse me. So what does that tell us? Well, what that tells us is that this choice of epsilon divided by 14, which comes from this idea that the absolute value of 3x plus 5, or 3x plus 5 itself, would be less than 14. Here we can see the absolute value statement above in the notes. All right. Is going to be a choice for delta. It's going to be a good choice for delta. Right? And we might say, why? Well, let's set this up. What we're going to say here, and this is always true in the quadratic case, this upper boundary of 14 on this absolute value, 3x plus 5 or 3x plus 5, right, which gives us this result right here, is going to indicate this low end boundary is going to be part of our algorithm for the choice. And I do say algorithm for the choice because it is a bit of a process we have to go through as we make our choice. Right? We are going to be looking at a scenario where epsilon could be any value greater than 0. So what we want to establish is that we do have a corresponding value of delta greater than 0, where our choice for delta, when we go to make that choice given a value of epsilon, is going to be based upon this argument here. We're always going to assume delta is going to have to be less than or equal to the value of 1 in our choice. Under that assumption, we're able to establish that our choice for delta should be the minimum value given by either the value of 1, right, or the value of epsilon divided by 14, this smallest possible value for epsilon divided by the absolute value of 3x plus 5. Right? This is how we're going to go about choosing our value for delta. Right? For any given value of epsilon. And what we now have to work through is the proof for epsilon values that are going to cause these given values of delta. Right? Or we got to work through the cases for these two choices of delta in a sense. So I go on to say, here's the proof. We've done all the algebra above. We're going to reference that here in the moment. But what we note is for every epsilon greater than 0, there must exist a corresponding value of delta greater than 0. Delta, where we're going to choose the minimum of 1 or epsilon divided by 14, such that this statement here, the absolute value of x minus 2, being less than our choice for delta, ends up implying that we have this. The absolute difference between f of x and L is going to be less than our given value of epsilon. right? That's what we have to prove. Now, here is where the proof divides itself into two parts. If we're given an extremely large value of epsilon, which is likely not going to happen, but we have to account for every possible epsilon greater than 0. So if we're given an epsilon that is greater than or equal to 14, what we're going to choose is the value of delta given by the minimum of 1, or that value of epsilon divided by 14. Now, if epsilon is greater than or equal to 14, the choice is going to always be the value of 1. If it's 14, if epsilon is 14, 14 divided by 14 is 1 in value. So it's going to be a choice between 1 and 1, and it'll be 1, right? Regardless of really what we choose in that case. But if epsilon is greater than 1, let's say it's 15. Well, 15/14 is bigger than 1, and we would revert our choice back to the first choice we have, which is just the value of 1. All right? So we consider the case for epsilon greater than 14 to begin with, which will always have us picking a delta equal to 1. Right? When epsilon is greater than 14. Now, if we take note, in that choice, the absolute value of x minus 2 being less than delta would imply that it's also less than 1. Whereas since epsilon is greater than 14, epsilon divided by 14 would then be greater than 1, and we'd be able to say that the absolute value of x minus 2 would also be less than epsilon divided by 14, because it must be bigger than that value of 1. And what that's going to lead us to be able to say, for the case where delta equals 1, well, at epsilon divided by 14, we've established it's smaller up here than epsilon over the value of the absolute value of 3x plus 5. This is inequalities at work, folks, right? So that epsilon divided by 14, which is bigger than 1, must be smaller than epsilon divided by the absolute value of 3x plus 5. And if we bring that up, so when delta equals 1, the absolute value of x minus 2 must be less than this argument for epsilon over the absolute value of 3x plus 5, implying that the absolute value of x minus 2 times the absolute value of 3x plus 5 must be less than epsilon, which we have shown is equivalent to the above statement, right, through our initial algebra in the proof, which is the corresponding statement for the absolute value of f of x minus L being less than epsilon, right? We have shown that for our first choice of delta equal to 1, that happens when epsilon happens to be given to us with a value greater than or equal to 14, that this result will always occur when the absolute value of x minus 2 is less than that value of delta. All right? What we now have to consider is the cases for when epsilon is less than 14. Right? As we say here, the proof is complete for when epsilon is greater than or equal to 14. However, it needs to be proven for epsilon less than 14. In this case, when we choose delta equal to epsilon divided by 14, when the minimum value is given by, right, the value given by the minimum, okay, be careful here. It needs to be proven for when epsilon is less than 14. That's where I'm getting lost, right? We need to choose a delta that's that value of epsilon divided by 14, which will end up being the minimum of this choice here, right? Because if we pick something like 13, which is less than 14, we'd have 13/14. And that's smaller than 1. This would become our minimum. Right? For any of the epsilons we're given that are less than 14. So there's the logic in our choice. which implies that delta equal to epsilon divided by 14 is less than 1. All right? So we're able to make this statement here. That absolute value of x minus 2 being less than delta, which we're choosing to be epsilon divided by 14, must be less than 1 because that epsilon there has to be less than 14. Something like 13. All right? Or we could just end by saying the absolute value of x minus 2 must be less than 1. Or what can we say about 1? Well, it was shown algebraically in the work above that this implies the epsilon divided by 14 is also less than epsilon over the absolute value of 3x plus 5, right? Or if we think about going back to this choice here, right, we're able to say that must be also less than epsilon over the absolute value of 3 plus x plus 5, and gives us this result here. Again, implying that we can write that statement as this seen here, right? Which we've shown with the algebra above can be expressed as this statement here. And thus, we can say this in that case of our choice. All right? This is a little power that happens in the case for inequalities. All right? When choosing epsilon divided by 14, right, we are delta equal to epsilon divided by 14. We are saying the absolute value of x must be less than epsilon divided by 14, which is less than 1. And we've shown that when the absolute value of x minus 2 is less than 1 with the algebra above, right, that absolute value of x divided by 14 must be then less than epsilon over the absolute value of 3x plus 5. So that allows me to go back and say that because we said that we're less than this initially, we must also be less than this initially. Again, in this case, again implying from the algebra above that we can draw this implication from the statement that the absolute value of x minus a must be less than our choice for delta. That is the epsilon delta definition for the case of the proof for this quadratic, right? The limit as x approaches 2 in the function 3x squared minus x minus 10 does equal 11, and we have just proven that with the result given above. We have just shown that for any choice of epsilon, in the case when it's greater than or equal to 14, we're going to pick 1, and in the choice when it's less than 14, we're going to pick epsilon divided by 14. There exists a corresponding value of delta that we just described, such that the absolute value of x minus 2, the value of x minus a, being less than that choice for delta, will always produce the absolute value of f of x and L's difference being less than our given value for epsilon. And we did that through some inequality relationships, folks. This proof relies pretty heavily on some inequality relationships. All right? And certain factors being true along the way. All right? In the end, it does take up a little bit of vertical space you can see here. But I do try to lay it all out for you in proper explanation. All right? So that is another example of proof, folks. Proof of a quadratic, at least, where I think if we understand these two situations, the case for the proof for a linear and the case for a proof of a quadratic, we have what we need to really appreciate what's called the epsilon delta definition of a limit. All right. I'm going to end there. We are going to come back. We have to talk about the some precise definitions for infinite limits and limits at infinity. So that's going to be the next thing, next couple of videos that I have for you. And I will see you next time with those.